In a previous class, we talked about how we can use modes to understand the response of multi-degree of freedom systems. And we saw that this 2-degree of freedom system we could see in two ways. In the modal domain, we would see that the response of each modal coordinate, that's what the in is here, the response of each modal coordinate would behave like a 1-degree of freedom system. It would have a peak near the natural frequency of that particular mode. And again, it would just be 1 degree of freedom. That's the only peak at all. We saw, though, that when we go to physical domain, so now if we're looking at x1 and x2, which are the displacements of these two masses, that the response that either response has both modes in it. So measuring on mass 1, we see a peak for mode 1 and a peak for mode 2. And so both modes respond at both of the masses. And that's why, in general, the response of any 1 degree of freedom on a multi-degree of freedom system can be complicated. It can have lots of frequencies in it, lots going on. But in any event, we can understand this using the modes, because in modal coordinates it's just 1 degree of freedom systems, and in physical coordinates we're just using the fact that the modal coordinates are related to the physical coordinates. Oops, sorry, I got this backwards. The physical coordinates are related to the modal coordinates by the mode matrix. So we're just adding these things up, and we talked last time about the fact that this is like taking mode shape 1 times eta 1 plus mode shape 2 times eta 2. So we're just adding that up. And each of these peaks, so at this peak here, this is the first element of mode 1, the second element of mode 1, multiplied by this function here. All right. So that lets us understand what's going on with multi-degree of freedom systems and why we see what we see. So in this lecture, we're going to turn that around, and we're going to see how we can use that to flip the problem around. Given a set of measurements, how can we figure out what the modes are? And this is called experimental modal analysis. And this is something that's used all the time in industry to take measurements and to make sense of them. So the most basic approach is really what we've described already. We measure some FRFs, such as this one right here, frequency responses. We identify the natural frequencies as the frequencies where those peak, and we can use the width of the peaks, or the half-power bandwidth method, to figure out what the damping is. So this would give us zeta 1, this would give us zeta 2, right? This would give us omega 1, omega 2. And so that takes care of the natural frequencies and the damping. And what about the mode shapes? Well, we can use the height of the peaks across many sensors to get the mode shapes. And so we'll spend some time talking about that to make sure that concept is clear. But again, it comes from the equations we derived last time. And as we said before last time, if we're just looking at the response and we've applied some force F, and we're near omega equals omega 1, well, near omega equals omega 1, these two things are going to cancel. So this one will be small. We'll have a small denominator. I guess I should say that's just the denominator. This denominator is going to be large, or normal size, I guess we could say. So this whole term we can say is negligible. And so near the resonance for mode 1, that's what allows us to use the peak and the half-power bandwidth to figure out what this mode is. And near the resonance for mode 1, notice that this then becomes x1, x2, and these would be in the frequency domain complex amplitudes. That ends up just being equal to some constant that has the denominator here, and it has this term in the numerator here, some constant times mode shape number 1. So the steady state response is just proportional to a mode shape. So if we need the mode shape, we can just grab x1, x2, and up to a scale factor, we know the mode shape. All right, so that's the basic idea. And this works great, and this is used all the time in industry. I guess I could also add that, there are more advanced versions. More advanced modal analysis. Maybe the main difference is that here we might actually use a least squares algorithm. And rather than just use peak picking, we could actually use least squares to fit this function with multiple modes, to fit this function here to the data. And that'll give us more reliable, more accurate natural frequency damping and everything. But the basic idea is the same, that all of these modal parameters are represented in the response. This basic approach is an easy way for us to pull those out of data, and people use this all the time. And you can also use more advanced methods, optimization, to actually figure out the best fit of those parameters to some data. So in all of this, there's one potential problem that can come up. And let's say that omega 1 was equal to omega 2. We had equal natural frequencies, right? If we did, then basically these two denominators are the same. I guess we would also need zeta 1 to be equal to zeta 2 technically for this to work. But those two denominators are the same. And so if that happens, our transfer function matrix, and notice that I've factored out the force. I've canceled that out of both terms because this is true for any system. But if we factor that out, we can basically combine everything on one denominator. So we get the two mode shapes. Oops, this would be mode 2 in the numerator, and then our denominator would be the same. So notice that the denominator is what leads to the shape. So it's hard to see that there are two modes. There's still going to be just one peak. If we were to look at the frequency response, it would look like one of these. There'd only be one peak in the response. And so looking at any one point, we wouldn't really have any evidence that there were multiple modes there. So we need some other strategy to deal with that. So let's talk about the different strategies that can be used. One approach is, there are multiple different kinds of experiments, and it all depends on how many points we think we can measure, how many response points we could measure at once. So the first case is kind of what I've described above. This is SIMO, or single input, multiple output. So in this case, we're going to apply a force at one point, single input. So let's say we apply a force to the first mass. But then we're going to measure the response at all of the points. So we're going to have x1 and x2. And you could generalize this. You could apply the force at any point for a for a multi-degree of freedom system. So if we do that, remember that up in the numerator up there, we have this term phi1 transpose f. So if we do that multiplication, what we'll get is phi11, phi12, if that's the, or phi21, this is the first mode, times 1, 0. Or in other words, the only thing that survives here is phi11. And in general, we'll write that as phi p1, or phi pr, where p is the drive point, or the point where we've applied our force, and r is the mode number. All right, so if we do this, our h of omega up above let's see. Our h of omega, this will just become phi p1, and this will become phi p2, and those should be the mass normalized phis. And this becomes a vector h. We get a single measurement at each point on the structure. And so in this case, again, we can say that h of omega, for omega approximately equal to the first natural frequency, will just be some constant times phi1, and that constant will be phi p1 over, well, this will have gone to 0, so we'll just have an I omega 2 zeta 1 omega 1. All right, so the mode shape is just proportional to the measurement that we take, and the constant of proportionality is here. And notice one really important fact: we need phi p1 to be non-zero for the mode to appear. And we also need the damping to be light. If the damping was too heavy, then rather than a sharp peak in the FRF, you know, we might get something like that where the mode could fall below the noise. But if those two cases are met, we'll see the mode. And so on our structure, if we go back to that bridge example, you know, let's say we're trying to measure modes of the bridge, and say we're trying to measure some higher order mode like this. If we apply a force here, then this mode doesn't appear, isn't excited. But if we apply a force at pretty much any other point, then we can capture this mode. All right, so that's one of the basic concepts in modal analysis here, to choose the excitation point such that our mode shows up, and then we can go and we can use all of the process we've talked about already to get the mode out. So that summarizes the single input multi-output test. The corollary to that is what we call the MISO test. MISO, or multi-input single output. We'll see that this one's practically the same, but it has different equipment requirements. So in this case, we applied a force at a single point and we measured the response at multiple points. Here we'll do the opposite. So let's say that we measure the response at only point P. So we're only measuring at point XP, but we're going to do several different tests where we'll sequentially excite the structure at different points. So in the first test, we might excite the first degree of freedom. In the second test, we'll excite the second. In the third, we'll excite the third, and so on. So if we were to do this, we'd just get a single value of the transfer function. So the first test would give us something with phi PR, because this is our response point. That's a scalar now, right? So we're getting only the first row of that matrix up there. And then we'd have phi R transpose, and then the force vector, which is 1, 0, 0, right? Or, and then we'll have the denominator, the same as before. So basically that just becomes phi PR, phi 1R. And then in our second test, we move the force to the second point. And you can see then, so we'll have 1, 0, 0, like that. Again, the denominator. So this, the numerator, and again, we've always got the denominator on the bottom. So in this case, we'll have phi PR, phi 2R over the denominator, right? And so we can keep on going. And what if we collect all of that data together? We put it all into a vector. So HP for the first, HP for the second, and so on. We could write the whole matrix as a summation over the modes of phi PR, and then we'll have a vector phi 1R, phi 2R, a row vector now. And then we'll have the same denominator, omega r squared minus omega plus I omega 2 zeta r omega r. So notice this is exactly just the transpose of the the single input multi-output test. So MISO and SIMO, they're both they give the exact same information, just transposed. Another way of thinking of this is if we think of the entire H of omega matrix, if we could measure everything, a SIMO test gives us one column somewhere in that matrix where the MISO test gives us one row. But because H is equal to H transpose, those two tests are equivalent. So that leads us to the last type of test that we might do, which is the MIMO test, multi-input, multi-output. And in this one, we might apply, in this case, we're going to measure at all points, or all the points that are of interest, and we'll apply forces at multiple points. So for example, we could apply force F1, we could apply a force F2, and so on. And we don't have to necessarily apply all of those forces at the same time. We could do this sequentially. As long as the system doesn't change from one test to the next, we can treat the data the same. And sometimes the forces are applied simultaneously. But anyway, if we go with this approach, we end up measuring a matrix of transfer functions. And we can write that matrix as some residue matrix over our denominator again. And this residue matrix AR is a matrix where we have each mode vector So here's the first mode, and then we have whatever the first drive point is times that mode again, and then we could also have the second mode, and the second drive point. So let's see. So this is, let's just write this for mode 1 at first. So the residue matrix for mode 1, we'd have the first drive point for the first mode. This is the first mode again, but the second drive point. So the second index is the mode number, and so on. So anyway, we can show that that matrix is equal to the product of a column vector, which is the rth mode in general, times a row vector that has that same mode at all of the points that were tested. So this assumes that we apply F1 on DOF1 and then F2 on DOF2 and so on. And in general, you don't have to apply them sequentially. You can skip any degrees of freedom that you want. But the important thing to notice is that this is a rank 1 matrix. So we actually can use that as a way of detecting whether there are multiple modes at any given peak in an FRF. So if we take some measurement and we have lots of different peaks in that measurement, and we look at one of those, if we have a matrix of data, we can actually look here and see, is the response governed by a rank 1 matrix, or is there a higher rank than that? The way this is done practically is to use something called a mode indicator function, or MIF, they're sometimes abbreviated. And there are lots of different ones. I'll just tell you about one of them that I like best, and they all seem to be pretty interchangeable. But the complex mode indicator function, or CMIF, the way it works is basically we take this matrix H of omega and we decompose it in this way into a matrix U, a diagonal matrix S, and a matrix V transpose. And this is done using what's called singular value decomposition, or SVD. And that the SVD algorithm gives us the property that the matrix we get out, U, will be orthogonal. So U transpose U will be an identity matrix. And the same with V. V transpose V will also be an identity matrix. And then the matrix S has the terms in order, such that we have S1, S2, S3, with S1 greater than S2, S2 greater than S3, and so on. So the reason this is useful is you can show that this triple product up there is equivalent to writing a summation of column Uj times column Vj transpose times singular value Sj. So notice this has the exact same form as what we saw up there. So if we have a single mode, this decomposes the response into a rank 1 matrix, into two vectors that we can use to build a rank 1 matrix. So if we have only one mode present, we expect to have S1 non-zero, and S2 equal to S3 equal to ... equal to 0. And in practice, they won't be precisely 0, but they should be smaller or negligible. And so this is a way that we can address difficult systems where we might have many modes present at one frequency. Let's show an example of this. So let's say that we have our two-mass system again. So this was our system, only I'm going to break it here. I'm going to make this spring approximately equal to 0. We could even make it exactly equal to 0 if we want. If we do that, the two masses are uncoupled, and actually the modes can be anything we want them to be. But we can show that one valid set of modes is still the set that we had before. So where the first mode vector is 1, 1, and the second mode vector is 1, minus 1. All right, so let's see what happens if we do that. So if we have the case where we have two natural frequencies being equal, we saw here, right, near the first resonance we could neglect one of these terms, right? Actually, I guess we saw that right here. If we have two modes equal, then we won't be able to tell that there's two modes there, right? So here's our expression for the transfer function. Well, if we take just the numerator of that term, so let's just say h of omega the vector, and this is in the SIMO case, that h of omega vector, it will have, in this case, we'll have 1, 1 times 1, the same vector transpose times the force. So let's say our force is applied to degree of freedom 1. And then for mode 2, we have 1 minus 1, 1 minus 1 times that same force. And all of this would be over the same denominator that we had earlier. All right, so if you work that out, what we're going to get is just the first, or just these two columns added together. So we get 1, 1 plus 1 minus 1 over the denominator. Or we get 2, 0, right? So that seems to be our mode shape. It seems to be that we have motion in mass 1, but we have 0 motion in mass 2. But notice that if we had moved the drive point, if we had the exact same thing again, but our drive point was now the second point, look at what happens in this case. In this case, multiply this one by a minus 1. In this case, our mode shape ends up being 0, 2. And what we see is that the mode shape seems to change with drive point. So that tells us that there's something wrong, and this complex mode indicator is a way of quantifying that. Right? If we apply multiple drive points together, if we applied both of those in a multi-input, multi-output test, then we would have a matrix 2, 0, 0, 2. This would be our residue matrix, this AR matrix. And obviously the rank of that matrix is 2. It's obviously full rank. So we would see that there are 2 modes present there. And so I'll show you an example of how this is often used. And I can show you this in MATLAB. And the problem is that of a simply supported plate. So we have pins on all sides, a plate that's pinned on all sides. And the plate is almost square, so that we have many modes with equal natural frequencies. So we'll see pairs of modes like that. And so let's flip over to MATLAB and we can look at this. And you've got this on the course website. And basically it has an FRF matrix that that's loaded in. And if we look at it, there's 81 measurement points. So there's a grid of points all over the plate like this, and a second row and a third row and so on. So there's a 9 by 9 grid of points, gives us 81 points. And there's 3 input points. So 3 different points on the plate were chosen as inputs. So what this first plot does is shows you what the FRF might look like if we just measured it at one drive point. And if we zoom in a little, here are all the different modes. And from this, there's no indication of whether they're close modes or not, right? if the frequencies are close enough, we can't see them at all by looking at this. They're so close together that there won't be two peaks. For example, I think this is actually two peaks, two modes in that. But they're so close together that you can't tell them apart. And that's kind of what we see through the theory here, right? That if we're only looking at a single point, if the frequency and damping are equal, we can just put this on a common denominator. And the only evidence is in the numerator that there might be more than one mode present. Okay, so then we compute the CMIF using a function given on the course website, and we'll look at the CMIF is going to create a plot. So let's look at that. So here's the plot that it creates, and it's plotting the singular values, those S sub j, 3 singular values at every single frequency. And here it becomes really obvious right away where the repeated modes are, right? This first peak, it says there's one shape that's dominant, and then everything else is really, really small. Where at this second peak, there are 2 shapes that stand out, right? And they even have maybe slightly different frequencies. So you can see there are 2 modes there with similar but not quite identical natural frequencies. And so this CMIF is a very powerful tool for identifying that. So we can see 1 mode, 2 modes, 1 mode. Here it looks like there are probably 2 modes at both of those peaks. And so we can see that right away. So these next couple figures are going to show you what you would get if you did a SIMO test at the 3 different drive points. And we'll look at this for mode 1 at, let's see, 19.7 radians per second. And we'll also look at it for mode 2 at 49.5. So that's what these 2 figures show. So for mode 1, it doesn't matter where we apply the force, any of these forcing points, we always get the same shape. And so that's at 3 hertz there. In contrast, we go to 7.8 hertz, right? So that's this frequency right here. And here we see we get this mode shape if we apply a force at one point. If we apply it at a different point, the mode shape seems to change. And the third point gives yet another mode shape, right? And that's the same thing that was happening here theoretically, where the mode shape seemed to change depending on where we applied a force. And that's because it isn't one mode, it's a linear combination of 2 modes, and we get a different mixture of those modes depending on where we apply the force. So the CMIF is just a way of measuring this and detecting it, and we can use it to look at a lot of data at once and to figure out where repeated natural frequencies might be. All right, so you have that function on the course webpage. It'll be linked here on the class page. So so you can take a look at that, and that can be useful in making sense of tricky data. All right, that concludes this lecture. We will see you next time.